So yeah, welcome to session 5. So today we will non-dimensionalize the Navier-Stokes equation and explore it. Okay. So what are the scaling parameters that we can use to non-dimensionalize this? Okay, it says that the maximum velocity in the system given by capital U. So we can use that as a scaling parameter and dimensionalize velocity. Let us give the non-dimensional parameter V star. So it's V by U. Likewise, there is a characteristic length scale, say L. So the gradient is dou by dou R na, in general. So let us take R vector star is equal to R vector by L, where L is some characteristic length in the system. So how can you dimensionalize time now? Time star. So it's a scalar, sorry. What's the characteristic time in this problem? See, we know L, we know U. L is meter or displacement. U is velocity meter per second. So if you divide L by U, you will get unit of second, that is unit of time. So you can dimensionalize, non-dimensionalize using that. E by L by U. Okay. Now non-dimensionalize del star. What is del star? What is del? Del is gradient, right? It's dou by dou r of something, some scalar. So it's dou by dou x, dou by dou y, dou by dou z. So its unit is 1 by meter. To non-dimensionalize this, you'll have to divide it by 1 by L, where L is a characteristic length. Or it is L then. Likewise, when I'm taking double differentiative, del star square, that is dou square by dou x square of something, it will simply be, right? Pressure, how do we non-dimensionalize? Okay, let us just use some dynamic pressure. PD star is equal to PD divided by pi. Okay. Pi is some placeholder variable for now. We don't know what it is. It is some variable. Later we'll see what it is. Okay. Right now it's just a placeholder variable. So now you non-dimensionalize this Navier-Stokes equation using these scaling parameters, and you tell me what the dimensionless Navier-Stokes equation will look like. So take a couple of minutes to figure it out, and then I will solve it. So did you figure out how to non-dimensionalize it? See, I'll give you a hint. Say the first term in our Navier-Stokes equation on the left-hand side, it's just dou v by dou t, right? So this dou v by dou t, if you want to write it non-dimensional form, you know what is v, right? V is u into v star, and t is L by u into t. So it is just u into, and what is t? L by u into t star. So it will be just L by u into dou t star. So you will get u square by L dou v star by dou t star. Fine. Likewise, v dot del v, how you will non-dimensionalize it? V is what? uv star. What is del? Del is del star by L. And what is again v? U into v star, no? So this is just nothing but u square by L into v star dot del star v star. Similarly, you can do for all the terms. So what you will get is that, see, the first term dou v by dou t will be u square by L dou v star by dou t star. Second term will be u square by L, we just saw now, v star dot del star v star. Right hand side is what? Minus 1 by rho pi by L. Because pi comes with, we don't know the scaling parameter for pressure, no? Dynamic pressure. So we just used some placeholder variable pi. So PD is just pi into PD star. And you know del star, we have already seen that. So what does it reduce to this term? Pi by L. L star, PD star. And the another term will be mu by rho into u by L star, L square, del star square, V star. Okay, so basically what is the right hand side again? Right hand side is nothing but combining everything. Minus pi by rho L del star PD star plus mu u by rho L square del star square V star. So if you look at these two terms, left hand side and right hand side, you can cancel off L, right? Take u square common. So it's just u square into minus pi by rho del star PD star plus mu u by rho L del star square V star. Multiply rho L by mu u both sides. Okay. So here you square into something, and this right hand side also you multiply by Reynolds number. No, not Reynolds number, rho L by mu u. You will get Reynolds number, just wait and see. So left hand side is what? Rho L by mu u into u square. So V star. This is what you're getting, right? So basically, what is this? This is the convective or inertial nonlinear term. This is the viscous term. And what is this? Rho L U by mu. So this is the Reynolds number, right? So basically, you're getting Reynolds number into substantial derivative dv star by dt star is equal to minus pi L by mu mu del star pd star plus del star square. Again, what is Reynolds number? Reynolds number is just rho ul by mu or ul by kinematic viscosity, where kinematic viscosity is mu by rho. This you can represent as L square by kinematic viscosity by L by u. Okay, so this is the viscous time scale, units is time. And this is the convective time scale, just L by u. Okay, coming back, what is the equation we got? We got Reynolds number to dv star by dt star is equal to minus pi L by mu u del star pd star plus del star square v. Right. So this order is 1. This order is also 1. This order is also 1. Why? Because your non-dimensional is graph. So v star can go from 0 to u. 0 to u by u. Yeah, because I'm non-dimensional with respect to capital U. So it's order 1. Equation also. Here also. You're scaling the parameters so that it is between 0 to 1. So the order is 1. Okay. So basically this term order 1, this is order 1, this is order 1. Now let us take two limiting cases. The first is when the Reynolds number is very small. Say Reynolds number is equal to 0, 10 into 0. So left hand side will be what? Something of order 1 multiplied by 0 is equal to 0. And right hand side, this is order 1, this is order 1. These two will become 0 right hand side when these two cancel each other because it's a minus term here. So if this has to cancel, so this has to be 1 now. So pi L by mu has to be 1. Okay. Or pi is equal to mu u by L. So this is the appropriate scale for pressure. So our equation just reduces to, in case of Reynolds number tending to 0, minus del star Pd star plus del star square V star is equal to 0 as Reynolds number tends to 0. So this is Stokes equation when Reynolds number tends to 0. And the kind of flow is known as Stokes flow or creeping flow. Okay, now if you again dimensionalize this, what do you get? Tell me. Del star you write in terms of del PD star you would write in terms of PD, del star square, V star like that. Okay, so what do you get? Okay, so what is the dimensional form you get? Minus del PD plus mu del square V equal to 0. I hope you got this term, this equation. So what is our basic Navier-Stokes equation? Okay, to get from here to here, basically, how do you get it in the Navier-Stokes equation? So our this thing can be obtained, this kind of form of the equation, by setting rho equal to 0 in the Navier-Stokes equation. Okay. So basically what it means that rho is absent in our Navier-Stokes equation. Rho is absent, or density of flow doesn't matter. Okay, so when I was talking about the nonlinear V dot del V equation, what does nonlinear mean? This is a question you may have. Okay, so imagine there is some operator, okay, operating on X, that is Y, say, some operating on X. Could be some differential form, some algebraic form, whatever. So Y1 is equal to L of X1, Y2 is equal to L of X2. So if L of X1 plus X2 can be broken down as L of X1 plus L of X2, it is linear. Otherwise, it is non-linear. Okay. Now you try to apply this concept and try to show y v dot del v is non-linear. Okay. So take a 5-10 minutes break. Then we look at the other case where Reynolds number is very high, tends to infinity, and then we will draw comparison between these two. Now, same equation, you put Reynolds number tending to infinity, very high Reynolds number. So basically, what was our non-dimensional form of Navier-Stokes equation? Reynolds number into dv star by dt star is equal to minus pi L by mu u del star pt star plus del star square v star. This is order 1, order 1, order 1. Okay. So if this order is very large, say infinitely high, so this term anyway you can neglect because it's just order 1. But this can equal to this when pi L by mu u is of the same order as Re, right? If pi L by mu u, the same order of Reynolds number, okay. What is Reynolds number? Rho u L by mu. Mu gets cancelled. L gets cancelled. So pi should be of the order of rho u square. Okay. So this is the pressure scaling at high Reynolds number. And now if you convert it back to dimensional form, it is just rho dv star by dt star is equal to minus del star dt star. I mean, this is the non-dimensional form. If you convert it to dimensional form, you will just get, there would be a rho here, sorry. In dimensional form, it will just be rho dv by dt is equal to minus del vd. So what is the original Navier-Stokes equation? So to go from here to here, so basically this part, rho dv by dt. So to go from here to here, you just have to put mu is equal to 0. Okay. So in this case, rho is present, mu is absent. So it's a first order non-linear equation. Non-linear because of the presence of V del V term. But only one boundary condition can be satisfied. So to resolve this dilemma only, the boundary layer concept came up. To satisfy both the boundary layers. Okay. So I'll be just making some summary and some comments. And maybe next class we will go into the boundary layer and stuff. When Reynolds number tends to 0, it is what is known as Stokes flow or creeping flow. Here, what is the pressure scale? I is equal to mu u by L. The Navier-Stokes equation, rho will be absent. You set it to 0. It is density does not have any function A. And this is the form of equation you get. Second order linear PD because there is no V dot del V term. No? In dimensional form, it is just minus del PD. This mu del square V. The other cases when Reynolds number tends to infinity, consider this as inviscid fluid flow because mu is absent. Here the scaling goes as I is equal to rho u square dv star by dt star. Or rho dv by dt minus del PD. So I'll just make some comments, okay? It should be self-explanatory. Third term neglected. So the nonlinear term rho v dot del v is also not there. What does pseudo 3D mean? Most of our experiences tend to be rooted in high Reynolds number cases, especially with water, air, etc. So, in that case, we have neglected the viscous term. Okay, so it's just root dv by dt is equal to minus del pt. So it's first order, so only one boundary condition. It cannot uh, satisfy both the no slip boundary condition and the specified velocity far away boundary condition. Thereby, implicit approximation can't be valid everywhere. No matter how large the value of Reynolds number. Because no slip will be discarded. So to get around this problem, Randall came with the boundary layer concept. So this is the equation right for Reynolds number. Say I put it as equation 1. So what Randall said is that this equation 1 contains scaling assumptions that are incorrect in the vicinity of a solid object. And we need a second order equation to satisfy both the no slip and the specified velocity boundary condition. Viscous stresses are important in the boundary layer. close to a solid object. Okay. So basically, that's why like there'll be another scaling parameter called the boundary layer thickness, and the viscous stresses term will also come, and hence you can satisfy two boundary conditions. So we'll move into all that in the next class. And for today, I think that much is enough. Yes. Just go through this once, maybe. Enjoy the India Pakistan match tomorrow, and maybe next week we'll see. Okay. Thank you.